Okay. Hello again. Weather 6, air masses, and fronts. So, what we learned before was this. You already know this, that air pressure is low, it's cloudy, maybe precipitation. When it's high air pressure, sunny. So, we've got two air masses there interacting. So, the question is, what is an air mass then? Here's your answer. Volume of air defined by its temperature and water vapor. So, um, just a large mass of air with consistent, similar temperature and humidity throughout. And then they're named and classified according to their location, um, and whether they form over land or form over water. So they're source regions, and then how far away from the equator they are, basically. So if we were in class, I'd say, look at these two air masses forming in these two locations, and what can you say about them? And what you end up describing, then give you a second to think about it. But this one forms over land far away from the equator, so it's going to be cold and dry. And this one forms over water closer to the equator, so it's going to be warm and humid. Or if you like, you could say warm and moist. Meteorologists like to call the air, when it's very humid, juicy. So whatever word you like to use. Maybe we'll just stick with humid. So here in North America, these are our basic air masses that affect us. So you could look at each one. Our main ones are going to be MT, maritime tropical, maritime polar, continental tropical, continental polar, and you can see where they are. And just from the name, you could probably be able to describe them, what each one, properties of each one. And then the bubble is where it forms, and then the arrow is the direction that it moves after forming. And so it literally will take that air and move it to the new location. So if we look here, this just kind of describes each one. All right, so maritime tropical is going to be warm and moist. Continental tropical will be hot and dry. Then up here, as we get farther away from the equator, these will tend to be cold and dry, the continental polar, and then these will be cold and juicy if they form over the ocean. Okay, so if they form over land, they're not going to be humid because there's not going to be a lot of moisture to pull into the air mass. And then it'll move and it'll change as it moves to a new location, but it'll bring that amount of humidity and temperature with it. And of course, it's relative to the season, right? A cold air mass in the summer is not going to be as cold as a cold air mass in the winter. So, why do these air masses move? Two main reasons here we'll mention just kind of briefly. Global winds and the upper air jet stream. So first, we want to talk about the global winds on the planet. So for a second here, pretend that the Earth doesn't rotate. There's no oceans. I'm sorry, that shouldn't say no oceans. That should say all oceans, in fact. Okay, so let's pretend the Earth doesn't rotate. It's an all ocean planet and it's not tilted, so it's straight up and down. So it kind of looks like that. Okay, so where's the warmest place on the Earth then? It will be the equator. So the air above the equator is going to warm up and it'll do what? Right, it'll rise up. So we're really going to mainly focus on the northern hemisphere here, but it'll be the opposite, the southern hemisphere. So it rises up at the equator, and then in the upper atmosphere, crazy line, I know, but it would travel up there to the northern hemisphere, or to the North Pole, where it's colder, and then the air would sink there, and then it would travel across the surface, warming back up as it got back down there. And we could call this just one big circulation cell. Okay, so it rises at the equator. At the upper atmosphere, travels northward to the pole, sinks at the poles, either one, and then travels southward across the surface. The air is moving. Okay, and it'd be the opposite for the southern hemisphere. right? It would travel like this and then sink at the pole and move that way. So what we'd have at the surface then is our winds, surface winds, are going to be coming from the North Pole to the equator and from the South Pole to the equator. So if you were standing right there, I guess it's all ocean, so you'd be floating right there in your raft. The winds would be constantly blowing from the north towards the equator, okay? And just constantly circulating in that little pattern. So it would look kind of like that. A little bit better of a drawing than mine. So there would be low pressure there. We'll come back to that, right? If air is rising, right? If the air is coming from the south and coming from the north, meeting at the equator, close to it, and rising up. We already talked about that. If air rises, that's low pressure, right? Okay. And so we'd have these constant cells circulating. So obviously, those three things aren't true on the Earth. There is a tilt. It's not just oceans. And it is rotating. So what we end up having is the same kind of a circulation system, same setup, but three of them. So still rises at the equator, travels this way, but it only goes to about roughly 30 degrees and then sinks, and then it flows forward, or not forward, flows towards the equator there. And it's sinking, so it's going to sink there also, and then but the wind's then going to blow northward and then up and then back. And then there would be one more here. I didn't put it in because it makes it look confusing, but it would be the exact same thing as this here. Okay. Hadley cell. All right. And so this is where we get our winds from. So in this little block here from 0 to 30 degrees, we have the wind blowing from the north towards the equator. And then because of our friend, the Coriolis effect, it's going to curve the winds to the right. So they're coming from the northeast. So these are called the northeast trade winds. So, and these are the global huge winds, right? Locally, things will be different, but these are the big major winds that are traveling around the planet. So between 0 and 30, we have the northeast trade winds. Winds generally come out of the northeast. Where we are here between 30 and 60, we have what's called the prevailing westerlies because of this cell, the winds are blowing from the south to the north, and then deflecting to the right because of the Coriolis. And then again, it's opposite up there in the polar zone there. Okay. So because the winds are meeting here at this area, roughly the equator, we have a low pressure, right? So winds meet there and they rise up. And we call this the ITCZ, the Intertropical Convergence Zone. So it's between the tropics where winds are converging. And then because of that, we have low pressure. And what do we have at low pressure? Clouds. So around the planet, there's basically clouds the whole time at the ITCZ, a band of it. I'll show you a picture here in a few minutes. It's not always at the equator. Remember, the Earth is tilted, so we have seasons, so it'll migrate north and south of the equator, but it's generally in that area. All right. And then, so if we have low pressure there, then here's where winds are diverging away from each other. And so air is sinking then, right there. So we'll have high pressure across there, pretty much clear spots. And then that'll repeat with the low pressure meaning up there. Right on. So these are the doldrums and the horse latitudes. There's some horrific stories. So this, if in the old days, the trade winds, right, makes sense to think about when they used to travel across the ocean trading with giant sailboats. And so the winds would just blow them. But if you got stuck in between here in the doldrums, there'd be no wind, okay? And so they'd have to get the oars out and row those big boats. And there's stories of, in order to make the boats lighter, the ships lighter, they dumped the horses out into the ocean, so they earned the nickname the horse latitudes. True as far as I know. Okay, so ITCZ. So what we want to look at then is this, to make a little more sense out of this. It's going to be confusing. So right here, so we've got the Hadley cell, and then the Ferrel cell between 30 and 60, and then the polar cells. Same, this is the exact same picture I was just showing you. just another version. And here's yet another version. Okay, northeast trade winds. Okay, so the winds are blowing across this way, and here the prevailing westerlies are always pushing that way. For that reason, that's why the majority of our weather here in the United States comes from the west. Okay, and we watch the air masses move across from the west. Either coming out of the north or coming up here, but then they travel from the west across the east. Okay, because of these global wind patterns. So here's a pretty. This is a video. I used to have this animation. It's fun to watch and control, but there's a little video of it I found that. There we go. We'll watch a little bit of this. You can watch the rest on your own. Let's just let me go ahead. So you can, you're looking at the PowerPoint, hopefully, so you can watch the whole thing. But let's just get to this one part where it shows them in motion. Here's what we want to look at right there. So that's what we kind of want to see there in 3 dimensions. Hopefully that makes sense then to everybody. Air rising, moving northward, sinking, and then we'll see if they put in the other cells here. So it doesn't have all the cells in it. Okay, so that's our global wind patterns that are one of the things causing the air masses to move. So there's the intertropical convergence zone right there. So all the time, basically, there's a band of clouds around the planet at the ITCZ because winds are meeting there, converging, and then rising up. Pretty neat. And then these are the other spots where there's generally high pressure. So if we look at this in this sense here now, we want to throw in a couple polar jet streams, or a polar jet stream and a subtropical jet stream here, just to mention them here real quick. So it's the same thing we're looking at. These are the cells, and then in between we've got some jet streams where it's just upper air flowing. So if you look at this one here, here's the equator, and remember we talked about this before, where at the equator the warmer air, so it's thicker. The troposphere is thicker there, and then thinner at the poles. So we've already been over that. Yeah, there's the tropopause, the top of the troposphere, and then here's the subtropical jet, which is a river of air flowing through the upper atmosphere. And so in this situation here, it's coming right at us, out of the screen at you. So here's the jet stream. Then when we look at it from above, upper air flow of wind. That's average where it is in the summer. Here's in the winter, average maybe a little farther north than that. But what it ends up doing is then sort of splitting air masses, and so we can have a cold air mass above it, north, I should say, not above, north of the air of the jet stream, we have a cold air mass. South of it, we have a warm air mass. So depending on what the jet stream does, it will determine the movement of the air masses. And so sometimes things like this happen, where the jet stream dips way down like that, and it brings that cold air. Sometimes in the winter, they'll say we have that Arctic blast. If the jet stream dips way down, and it'll get cold way down here. And then it's keeping the warm air masses south of it. And so we have cold air mass north of it. And they'll kind of ride along that. And then sometimes crazy stuff like this, right? There's a big high pressure center sitting there kind of messing with the jet stream, right? So the jet stream and the global winds are what moves the air masses around the planet. Okay, so as they're moving then, our next logical topic there is a front, and it is literally exactly what it means. If we could locate a front here, look right there. if we look at these are all temperatures in Fahrenheit on a weather map. You can see all these are here 40, 42, 38. We can see over here they're different. So this is a cold front coming through. So and we can tell because the temperatures on this side are all colder than the ones on this side. So a cold front doesn't mean that the temperature is going to change from like 80 to 30, right? Just it can even be this subtle. That's the cold front. So what is a cold front, or what is a front in general? Um, Literally right there, it's the leading edge of an air mass. So this right here would be a big cold air mass, probably a dry one moving in if it's coming from that direction. And then it's just the front of it, right? And as it moves through, it bumps into the warm air that's there. So we'll call it a cold front because it's bumping into warmer air. So as the air mass moves, that's the front coming through. So we generally have fronts are associated with low pressure centers. So here's low pressure. This little symbol here means a warm front. This little symbol here means a cold front. So we just got cold air pushing this way, warm air pushing that way, and different things happen when warm air runs into cold air and when cold air runs into warm air. Okay, so big, warm, juicy, moist air mass right there moving up out of the Gulf of Mexico probably. Here's cold air mass maybe coming from Canada, moving sort of around, right? It won't spin all the way around, but it'll move around as the low pressure moves from west to east across the country. So this would be a cool demo to do in class. We're not in class, so we'll watch a little bit of this. You probably have seen this before.
Hello boys and girls, and welcome to Hoopla Kids Lab, making science super fun and super simple. Today we're going to show you a wacky water experiment that I think is really clever. All you're going to need to conduct this experiment is a jar of cold water.
Whoops, didn't know that would happen.
A jar of hot water, some blue and red food dye, a plastic card, and a dish. Make sure that one of your parents is around to give you a hand with this experiment. The first step is to pour the red food dye into the hot water jar and then very carefully stir it.
So let's just move this along a little.
The first step is to put your cold water jar inside the dish.
Cold water.
And carefully cover it with a plastic cover. The next step is to turn this jar carefully upside down. You'll see that the vacuum formed inside the jar holds the card onto the surface. Then have your mum or dad place the hot jar of water into the dish and carefully place the cold jar on top. You'll need to go around every side of the jar and make sure that the edges line up perfectly. Then get someone to very carefully pull out the card from in between the jars. As they do, you'll see that the water starts to mix, which forms a pinkish purple colour. As each of the jars mixes in with the other one, you'll see that the colour evens out completely. This is because the water is very slowly mixing all of its molecules together. Now try this. Take the jar of red. This time the blue jar is on the bottom and the red jar is on the top. Have someone very carefully remove the card from the middle, and this time you'll see that the jars don't mix. So why is this? Is it the colours? No, it's not. In fact, the hot water...
So you've got the warm water on top. You probably know this. Warm water is going to be less dense, so it'll stay up there, and the colder water stays down low because it's more dense, so they don't mix. So when they do something like this is more specifically what we're talking about here. They do a very similar demonstration here with warm and cold water. Measure it. So we got the warm water over there, cold water over there. They're going to pull this little divider out and just watch it happen, I guess. It's short. So this is warm and cold water, but the same thing would happen with warm and cold air. So let's just notice right here for a second, the colder air is diving underneath, right? Because it's more dense, so it's pushing its way underneath, while the warmer, cold water rather, and the warm water is then riding over top because it's less dense. So this is just like a cold front, we'll say, moving left from right to left across the stream. Cold air is bumping into warm air, we can say, and it's going to be diving underneath it and forcing the warmer, less dense air up. And this would be our front right along there, and it would be shaped like that as we go up through the atmosphere. So now more specifically, this one will show exactly what happens with the two kinds of fronts, basic kinds of fronts here.
Precipitation happens at what are called cold fronts and warm fronts. These are weather systems that develop where the masses of cold air collide with masses of warm air. And the name actually comes from war, where armies would meet along a battle line called a front. And one way to think about looking at the cold fronts and warm fronts is to think about which mass of air is going to be in the battle line. So let's start with a cold front. This is a situation that happens where cold air moves in like a big wedge underneath the warm air. Cold air is always heavier than warm air, so it's denser, and it's going to tend to slide under the warm air and push the warm air upward. And anytime you have air rising upward, it's going to expand and cool and lose its ability to hold moisture. And this would give you a band of clouds and precipitation.
It's worth mentioning at this point, I'm talking about humidity a little bit. So cold air comes in, and so the greater the difference between the two, the more vigorously the air will be forced up. Okay. In addition, humidity plays a factor in there too. I would always ask this question: if I was holding a big pile of real dry air and a big pile of real humid air, which one would be lighter? And everybody always thinks it's the dry one, but actually, the more humid the air is, it actually becomes lighter, so and more buoyant. So that's why in the summertime, is the thunderstorm threat, right? Where we've got already in place warm, humid air that is already buoyant and wants, so to speak, to rise. And then as a cold front bumps into it, that air is ready to go, so it just rises up quickly. And the faster the air rises up, the more likely it is to create a thunderstorm.
On weather maps, if you watch the weather on the news, you see cold fronts marked by lines of days.
Notice that because you'll be looking at some of those later. Triangles mean cold front.
Typically have very intense local thunderstorms and rainstorms. So it might pour rain for a short time, but then quickly, usually within an hour or so, you get a so cold fronts is where the cold air pushes the warm air much higher than now the warm front has in common a couple of things with the cold front. One is that the warm air still goes up on top of the cold air, but in this case the cold air is up.
Let me point out something before he moves on. So look at how the warm air is going to move over top, and ride well ahead. If you were living like right here, underneath these real high cirrus clouds, this might be 2 or 3 days ahead of the warm front. And so you could actually look at clouds, and I'll show you a cloud diagram here in a minute, and give a rough estimate of the weather to come. So clouds mean different things. We don't just have random clouds forming randomly. They form at certain elevations for certain weather conditions. So in this case, when the warm air hits cold air, it'll ride over top of it and up and well out ahead of the actual warm front, like it's showing there.
Warm air pushes against the cold air, squeezing it out. Squeezing the water in the sea, and out. And as the air pushes, it also Blowing cold air, rising in
Clouds.
again, this is a short of the moisture to get clouds. Now along the north fronts, typically have more violent, more mellow, more spread out the rainstorm weather include local intensity. And if you're looking at the weather on the east, there are warm fronts on mass with hot fronts that might be the direction of the warm fronts pushing over.
Okay, so back it up one. So let's just try to make sense of this. Spend a few minutes looking at this. This is a pretty good little diagram. So here's a cold front moving, and so we're really looking at the side profile of it. So it's moving from the left to the right. Here's warm air, and there's cool air. So this is a cold front because it's cold air. A good dome, right? Because as it bumps into the warm air, it pushes it straight up. So we end up with heavy showers and thunderstorms right along the cold front, generally speaking, okay, as it's happening. When the warm air runs into the cool air, we get this little wedge shape, and where the warm air rides over top of the cool air, and we'll generally have then showers, longer periods probably. These are going to be more violent and short, right, depending on the humidity and the temperature differences, but these will probably be longer lasting showers out ahead of the actual front. Here's the front. When you notice, it would go through, and then the showers will be, the rain precipitation will be out ahead of it. So there's our low pressure. So this is our general setup here, United States. A warm sector, cool sector, and then the cold sector there around. And this is the warm front label, the cold front label. And so things you would notice around, oh, that's why that was like that. Things you would notice around, or as it moves through, obviously a change in temperature, right? If you were existing right here, where my cursor is, you would be feeling, see the wind coming from the southwest, okay? Warm, moist air coming from the southwest, all right? And then after the cold front passed, obviously then the weather's going to change. You've probably noticed this, no doubt, especially in the summertime. Nice, warm, juicy air out, and the wind's coming from a certain direction. Maybe you don't notice the wind direction, but you certainly would notice after the cold front, maybe there's a thunderstorm, and then afterwards, the air is cooler and maybe drier, right? It might not be so humid afterwards. And the wind, if you take note, will probably be coming from a different direction, but now you're in a different air mass. Literally, this air mass is now over top of you, so the cooler air is now where you are, okay? The same thing with the warm front. If you were up there, then afterwards you would notice warmer air and maybe more humid air after the warm front went through. Things to notice when you're checking out the weather from now on. So then here's a little graphic of the different cloud types if you're not familiar with them. High, middle, and low clouds, right? There's the thunderstorm cloud, fair weather cumulus clouds that just pop up as air rises up and puffs into the sky, or puffs into a cloud when it squeezes the water out of it. And then there's fog is just cloud lying on the ground. So I showed you that really to show you this. When we look at this, here's low pressure center, right? Cold front, warm front, counterclockwise around the low pressure. And then these are the locations, generally speaking, that these different clouds form based on the fronts. All right. So nimbostratus is just large areas of rainy weather. Stratus means layers, so just different elevations. Cirrus is real high up. Cirrus are the real high, wispy clouds. You come way ahead of the warm front. And then lastly, we can just say Tornado Alley, you've certainly heard of. Way more tornadoes here in the United States than anywhere in the world. And for this, we've got this perfect setup here of warm, dry air coming in here from the Mexican plateau, a warm, moist air coming out of the Gulf of Mexico, cold, dry air coming down here, and it all meets right in there. And with a little jet stream flowing in, some other conditions to make it perfect, and we get more tornadoes here by far than anywhere in the world. Thus the name Tornado Alley. And it largely is due to the air masses that meet there in that little area, and there's a lot of flat area for it to travel across. Tornado Alley. So, what you're going to do now then is another gizmo. This one should be hurricane one probably wasn't that hard. This one would probably be easier. And what you should see on this, what I would hope if I were watching you work on this or listen to you, I would hopefully hear a lot of, oh, that makes sense, because this should be all the same things really that we just talked about, or a lot of them anyway, just on a map. So it's going to look like this once you've launched it. It's called weather maps, and there's all these things to click on and click off, and it'll tell you what to do, whether you show the land or show the grid, okay? And it'll give you little maps or little, whether it's rain, mixed ice, or snow. And then you will use the weather maps sheet, student exploration sheet that's in the OneNote. Okay, talks about that a little bit there. Gives you some how to figure out the wind speed, and then you just go through it again, just like we've done before. Okay, weather maps. All right, so that'll all be in the OneNote all together. That'll be also, I'll have it listed in the Your Homework section as always. Okay, see you soon.